Here is a problem that we were studying, we were doing in last class. You see, what is the change of heat when we react carbon disulfide with oxygen to give carbon dioxide and sulfur dioxide? So we don't know how much heat is produced here, right? But we are given this data. If I bond carbon with oxygen, I get carbon dioxide, and from this reaction, I get 393.5 kilojoule per mole out. So the reaction becomes vessel becomes hot. Like this works as a fuel. We are burning the carbon fuel here to produce carbon dioxide and heat. Here, if we burn sulfur with oxygen, we are getting sulfur dioxide, and we are getting this much heat out. It works as a fuel. And if I burn carbon with the sulfur, so I think this is a plus here. Carbon and sulfur. Carbon disulfide is, sorry, this is not the one. Carbon disulfide is, how much is carbon disulfide here? Carbon disulfide is 87.9. 87.9 plus 87.9 kilojoule per mole. Kilojoule per mole. So this reaction, carbon, if I want to react carbon with sulfur, it doesn't happen yourself. We need to burn fuel from outside and give a lot of heat to it. Yeah. So this is endothermic reaction. This is exothermic reaction. This is exothermic reaction. Exothermic reaction meaning that it's like we burn fuel in car, or you burn fuel in home, like that. But to do this reaction, we need to heat something and put these two things together, and they only start to react. Yeah. So this is endothermic, this is exothermic, this is exothermic. So from these three data, we need to find how much heat would it produce or absorb here in this reaction. So like that. So how I do it, I arrange this equation, these three equations in such a way that I get this this equation. Yeah. So let's arrange that one. So what I have in the left side is CS2, right? This is my reaction. This is my target reaction. I have a CS2 in the left side, but in among these three reactions, CS2 is in the right side, right? So I must flip that reaction to the so that the CS2 comes to the left side. Make sense? Because you see here, CS2 is in the left side, but in this given reaction, CS2 is in the right side. So I must put this CS2 to the left side. So I'm flipping this last reaction first. So let's flip that reaction first. So flip this reaction, the third reaction first, like this. CS2, I'm flipping this one, CS2 this side, and CN2S this side. Make sense? I just flip the reaction, this third reaction. I just flip it so that it looks like more like this, right? See here, this third reaction, this one, I put this CS2 this side and CN2S this side, so it looks like this equation. So CS2, I put in the left side. Make sense? Good. So if I flip this equation, the value of heat also flips. So if it is a plus, it becomes a minus. This is very important for the lab number 11. So you will do that in lab. So this equation becomes now, this heat becomes now 87.9, negative 87. Why? Because I flip this CS2, I put this way, CN2S this way. So this, if this is a plus, this must be the minus. Yeah. If you flip the reaction, the sign of the heat also flips. If it is a plus, that becomes minus. If that is a minus, that becomes a plus. So I'm done with this one. So I'm done with this one. So now, what do I need here? I need sulfur dioxide, carbon dioxide, and sulfur dioxide toward the right side, right? So it looks like it's a good. So oxygen is in the left side. So I'm going to put this oxygen C plus O2 because I need O2 in the left side. So I'm just putting this reaction at such that gives me CO2 because I need O2 in the left side here in the target reaction. So I put the O2 in the left side. I need carbon dioxide in the right side. So I put that carbon dioxide in the right side. So I'm just trying to rearrange those equations to meet the target here. Make sense? So I didn't flip this. So it's just carbon, oxygen, carbon dioxide. So I didn't flip it. So if I had put this one this way, this one this way, I would put plus here. But I just copied that one. So this is just is minus 393.5. Because I'm just copying and putting there, right? I didn't flip. If I had flipped the reaction, I would put minus to plus, plus to minus. Now, so I'm done with this one. Now, what do I need in the left side? I need sulfur dioxide in the left side, or I need oxygen in the left side. I need oxygen in the left side. So I just write that as it is. So sulfur, I need sulfur dioxide this way. So sulfur plus oxygen gives sulfur dioxide. So just like that. So I didn't flip this one. So the heat is still 296.8 kilojoule, all kilojoule per mole. So make sense? So I'm just trying to find that reaction what it wants to find it, right? So I'm just going to erase all these three now, just to make space here. So this is lab number 11. You will do this one. So it's the thermodynamics we will be doing there. So now I'm going to add all these one, and whatever I don't need, I'm going to cancel them. If they don't cancel, I'm going to multiply with certain numbers so that they cancel. Yeah. So if you see here, this carbon is in the. I'm going to add this all. So this is in the right side. This is in the left side, right? So carbon can cancel. So like this, x is equals to, if you have x is equals to x, you can cancel left and right? Just like that. So I'm just adding those. So this is in the right side, this is in the left side. So left side and right side equal number cancel. Good. Now, do we cancel anything here? I want to cancel 2s with s. Can you cancel s and 2s? Can you cancel x is equals to 2x like this? You can't, right? To cancel exactly, you need to have a 2x is equal to 2x, right? So equal. So I just want to make the this guy 2s, so that this one and this one I can cancel. So what I'm going to do is I'm going to multiply this equation by 2. So I multiply this equation by 2. So I should multiply this by 2, and I should multiply by this 2, and I also should multiply by the heat by 2. Make sense? Yeah. So you see here. What happened? This is 2s in the right side, this is 2s in the left side. So I'm going to cancel this one and this one now. Yeah? So like this. Now I'm going to add all those three and I get that equation. So let's add those. So what I have here in the first is CS2. So I write CS2 here. What I have here is a 1 O2 and 2 O2 here. So this and this add. So that becomes 3 O2. 3 O2, O2, 1 O2 and 2 O2 becomes 3 O2, right? 3 O2. And then in the right side, I have CO2 here, and plus 2 SO2 here, 2 SO2 here. See here how I just, by adding these three equations, I got exactly the same equation I need. CS2, CO2, CO2, CO2 to CO2. I got that equation, right? Same thing? Yeah, now you need to add this heat together. So what is this one? So if you multiply this heat with 296.8 multiply by 2, you will get, how much you get? 593. Minus 593.6. So this gives you 593.6. This one. So 2 multiplied by this gives you 593.6, right? Now add these three heat together. So this is now gone. So this is my heat now. So add this one, and this one. That will give you 1075. Negative 1075. So I added this number, this number, this number, this number, and this number, and I get this kilojoule per mole. So for this reaction, the heat of formation or heat change or enthalpy change is 1075. So this negative sign is saying that this reaction work as a fuel. If you mix CS2 with oxygen, so buy some carbon disulfide and put in the table in some vessel, and then fire a little bit, and it just give a big fire, and it gives a lot of heat out. Make sense? So that's how we do. So it's just like arithmetic. So you just try a reaction, and if you flip, multiply. If you flip the reaction, just change plus to minus, minus to plus. If the reaction the coefficient doesn't come, or the things don't cancel, multiply the certain reaction by certain number, including multiplying that heat by the same number, and then those cancel, and you get the. Make sense? Okay. So you need to practice a couple of times, yeah? So now let's do one more problem and we finish the thermodynamics. So actually there are thermodynamics, a lot of things we study, but if you go to the laboratory and you do research, you don't have to understand that many things. You just go there and mix couple of things what you want to study, put in the calorimeter, like the coffee cup calorimeter, and record the temperature change and calculate the heat. So this is very simple, but in chemistry and general chemistry, they teach a lot of concepts. So yeah, so I don't think this kind of thing anybody do something like this in laboratory these days. So the coffee cup calorimeter and the Q equal to mCT2 minus T1, and mixing sodium hydroxide with water and recording the temperature change and applying the Q equal to mCT2 minus T1. Those formula are very important, yeah? So now let's do one thing here, and then we finish this chapter. We spend a long time for this chapter. So I posted the homework yesterday. So try those homework for 1 week. Now here is one equation. So it's just like this one. Calcium carbonate. This is solid. Calcium carbonate, and when you heat it, it breaks to give calcium oxide and carbon dioxide. So I'm in the 15th slide here. Carbon dioxide. So what is the heat change? So you take some calcium carbonate, which is a what is calcium carbonate? Like the marble we put on the floor, right? The calcium carbonate is a marble that we put in the floor to make it shiny, right? Calcium carbonate. And then if you heat that calcium carbonate, it breaks to give calcium oxide and oxygen. Now, what is the heat change here? Should it work as a fuel, or we need to put a lot of heat to break it? So fuel meaning that if you put a tiny bit of heat, it burns and it gives out a lot of heat, and we can use that heat to room heating, something like that, like burning wood, right? Is it a fuel, or is it something we need to put burn a lot of fuel to break this one? So we want to find that one. So how much is the heat change here, delta S? How much is the heat change? And the given number here are, so they are giving the, no, it's a carbon dioxide. I think this is a carbon dioxide here. Now, they are giving the heat change for this one. If you want to make this one, how much heat would change? If you want to make this one in the laboratory, how much heat would it take, or would it change? If you want to make this one, how much heat would change? So giving here. So if you want to make calcium carbonate, the heat change would be minus 1207.6, minus 1207.6 kilojoule per mole. And if you want to make calcium oxide, you want to put 635.1 kilojoule per mole. And if you want to make carbon dioxide, you want to put minus 393.5 kilojoule per mole. So, meaning that if you want to make a calcium carbonate from calcium, carbon, and oxygen, it gives a lot of heat out, like 12 minus, meaning that it is working as a fuel, like this one. So, let's say you have a calcium here, and then you have some carbon here, and you have some oxygen here, and you are mixing these three things and making calcium carbonate here, right? Calcium carbonate, like this. Make sense? Now, and if you measure the heat, you get 1207.6. You get a lot of heat out of this reaction. So if you want to make calcium carbonate in the laboratory by mixing calcium carbonate and oxygen by burning a little bit, it gives a lot of heat out. So it works as a fuel. So if you do this reaction, if you mix calcium carbonate and oxygen together and burn it, it gives a lot of heat and makes the room hot. It works as a fuel. That means that. Make sense? And then how about the calcium oxide? Let's look another reaction. So let's say you have a calcium here and you have oxygen here, and you go to the laboratory and you put a tiny bit fire or do something, and you just mix two together. You don't have to even fire this. So if the calcium is very, very pure and put in the room, it immediately catches fire and then the room becomes hot. So it also works as a fuel. So it CaO. So from this reaction, this much heat is coming out if we do that reaction. It's also making our room hot. Now, so what works as a fuel? Now let's look another one. So how about the carbon dioxide? Let some carbon, like the wood, and then put in oxygen. Carbon doesn't bond itself in oxygen, so we need a tiny bit of fire in the wood, right? Carbon is the wood. So coal. So we bond this, and it gives out the carbon dioxide, and it gives us a lot of fuel, like this much fuel, right? This much heat. Make sense? So this is the way we produce the electricity. So we buy a lot of coal from who produce the coal, and we bring the coal in the our powerhouse, and we burn the coal from carbon, mixing carbon and oxygen. It gives a lot of heat, like this, a lot of, and this heat we use to boil the water, and then the water vapor comes, and water vapor will rotate your turbine, and it gives the electricity. Make sense? So this is also the fuel. Carbon is a fuel, right? Coal is a fuel. So all these three things are giving out the heat. So if that is the case, these three numbers are given. So this kind of the number you can find in the book. A lot of other people have done this kind of reaction and collected this data and put in the book. Yeah. So this coming from the book. Now we need to find this one. So maybe you don't find this thing in the book. So how much is the heat change in this reaction? So it's pretty easy. So if you want to look the heat change for this reaction, this is the total heat reaction change. We write delta H is equals to sum of product minus sum of reactant. So that's how we calculate. This is heat. Sum of the product side minus the sum of the reactant side. Now let's look the sum of the product side. What is the sum of the product side is CaO. Product is this side, reactant is this side. So sum of the product. So CaO, I have this much, minus 635. So this is minus 635.1. So that's this for this one, that one is. And then this one for carbon dioxide is also product side. So minus 393.5. So this is the sum of the product side, right? So I'm just putting those numbers together. And you put a minus sign here. This is a minus sign here, and sum of the reactant side. So the reactant is this one. There is only one reactant. So sum of the reactant is just this number. So that is minus 1207.6. So put all those numbers in calculator, and calculator will give you the answer. Yeah. So that will be plus 199 plus 199 kilojoule per mole. Make sense? So what does that mean? So if I want to break this one, I need to bond the fuel, and I need to put that heat to calcium carbonate, and only it bonds. It is not working as a fuel. Breaking of calcium carbonate to calcium oxide and carbon dioxide is not working as a fuel. It's not giving us heat. So what we need to do is we need to find the wood or the gas from outside, and we bond the gas or wood here, and then we need to dump calcium carbonate there, and only calcium carbonate breaks into calcium oxide and carbon dioxide. Make sense? So this reaction is not a fuel. This reaction is not working as fuel. It's consuming our fuel. It's a plus sign here. Make sense? So it's like that. Already. So suppose I have something like this. If I have to, this is already balanced. Sometimes it's not balanced. Maybe you have to balance by putting 2 here. I'm just assuming here, yeah? It's not, it's already balanced. So if there is a 2, what would you do? So you would multiply 2 CAO, meaning that you'd multiply this number by 2. 6351 multiply by 2, and you would put that number here. So if there is a different coefficient here in the balance reaction, so you need to multiply that. Suppose this was 4 CaCO3 in balancing in the by coefficient, or 2 here. So what would you do? So you would do CaO is 1 here. So CaO is 1, already given 6 field. This is good. Now it's 2 CO2 here. So CO2 would be 393.5, but in coefficient here is 2. So you would multiply this number by 2. And you would put that number here. Make sense? And then here there were 4 CaCO3 in this reaction. 1 CaCO3 is 1207. You would multiply this number by 4, and you put that number here. Make sense? So we have to just do some arithmetic there. If there is a more number, we need to get a more heat, right? Make sense? So if you have a 1 gram calcium carbonate, you get it's a kind of, so 1207. So actually calcium carbonate is 100. If you have 100 gram of calcium carbonate, if you are making 100 gram of calcium carbonate from calcium carbon and oxygen, you will get this much heat out. So if you had 400 gram like that, so how much you would get? Multiply by 4, right? So if there is a coefficient, if there is a coefficient here in the balance, you would multiply this heat by those coefficients and put those numbers there. Yeah? Make sense? Good. So I think we study a lot of thermodynamics, almost 7 lectures. So it's a lot, but don't get afraid. In exam, I will tell you what kind of problem I will put, because this is too much material, right? I can't just teach what I want to ask in exam, right? So we need to study a lot, but in exam, we don't study everything. So some of the students who are really good background in chemistry already, so they may want to try everything. They may want to learn more, but maybe somebody is just starting, they don't want to study everything, right? So I'll tell you what kind of problem there will be in the exam. So I think we are done with the chapter 5, so we are in right time. So we just have 4 chapters left, so we have plenty of time here. So let's do chapter 6. Chapter 6 is it's a little interesting also, and it's a little bit non-intuitive type. So first of all, we talk about the electromagnetic radiation. So electromagnetic radiation. This is chapter 6. So we are working with the electromagnetic radiation. Electromagnetic radiation. So pretty much what we are doing these days in the laboratory are using the electromagnetic radiation. For example, heat. So if you are heating, so it is kind of the electromagnetic radiation. So heat. So sun is giving us heat, right? Sun is up there, and this is giving heat. So that how does the heat come from sun to us? It's a kind of the wave. So that is called the electromagnetic radiation. Yeah. So X-ray. So you go to the hospital and do the chest X-ray or something like that. So what is taking the X-ray, the photo of our bones and muscles? So that's a electromagnetic radiation. And infrared light. So infrared light is just like the heat. So if you are just sitting in the couch and turning on the TV with your remote control, so you are just giving some infrared radiation to the TV from your remote control, and TV either it turns on or it turns off. So that's also electromagnetic radiation. And then the microwave. So you go to the kitchen and you turn on the microwave, and the water becomes hot. So what is making the water hot? So the microwave produce some wave, they call microwaves. So the microwaves when fall into water, so they make the water hot. Yeah. So these all kind of thing are the electromagnetic wave. Light. So we are turning on the light here, and we are seeing this light, and this all light is also called the electromagnetic radiation. Whatever you see in the laptop and all these things is coming from the electromagnetic radiation. So this kind of thing are called electromagnetic radiation. They have the electrical properties as well as they have the magnetic properties. So we call them as electromagnetic radiation. Why we call the electromagnetic radiation to something? Because they produce electricity and they produce or you can say, oh, they can interact with the magnetic field, or they can interact with the electrical field, or you can easily say that, oh, it can produce the electricity. If light falls on something, it can produce the electricity. So we call these rays, or these things are electromagnetic radiation. Make sense? So why these things are called electromagnetic radiation? Because they can interact with the magnetic field. So they behave as a magnet, and they can interact with the electrical field, meaning that they can produce electricity. They can change the direction of the electricity or something like that. So these are called electromagnetic radiation. All right. So now electromagnetic radiation travel as a wave. Just you go to the lake and just sit there, and the water is traveling like the wave, right? The rising and the falling, and the rising and the falling, right? So I used to live in Milwaukee, and I used to go to Lake Michigan and stand there and look the wave, just rising and falling and rising and falling, right? So how the water travel in the lake, just like that, the electromagnetic wave travel like that. Yeah. So just like this. So let's say you have a heat source here. You are burning something here. This is a heat source. So you are burning something here. This is an oven, right? Now you are sitting here. You are sitting here. So you get the heat from here to here. So how does the heat come to you from the oven? So it's just like this, just like the wave, like this, just like the wave. Make sense? It travels like this. Yeah. So how does the sun comes from sun to earth? So like this. So you have a sun here. You have a sun here. So the sun is giving heat and light to us. So the heat and light waves comes like this. Maybe this is a heat. This maybe the sun is giving us the heat like this. But if it gives the light, maybe like this. So both ways, you see that? So here the sun is sending us the heat by like long, like how the big man walks, like the long leg man walks, right? The heat travels like this. But how about the light? Maybe the light is like this. So maybe this is a blue light, or maybe white light. I don't know. So if it is a light travel like this with a very small distance between this peak to peak. But is a heat, the heat travels like long distance, like this is a man with a long leg, this is a baby with a short leg, right? But this walks fast, this walks slowly. So I'll talk about that. Yeah. So the heat and light comes at the same time. So if you switch on something, the heat and light comes at the same time. So like that. Good. So these are this kind of the energy travel in the wave like this. So I just told you the energy travel in the wave like this. So now we need to what are the properties? Some of the properties of the of these waves to identify them. So the distance between this peak to this peak is called wavelength. So it is given by lambda. So the light, electromagnetic radiation, whatever everything is just move like the water wave, like this, and you have the peak and the valley. So this is a peak and this is a valley in the wave. So the distance between the nearest two peaks is called the wavelength. WAVE, wavelength, and it is given by the lambda, the Greek letter. All right, so lambda. So this is one property of the wave. Then another is a frequency. So frequency is a like this. So how I just okay, we'll talk later. So this is the wavelength. So this is given by the lambda. Now we have another property of this one. This is called frequency, given by nu. This is frequency. So if the distance between this peak to peak is very large, frequency is very low. But if the wave is like this, you see here, so the distance between this peak to this peak is very large, so the frequency is very low. But the distance between peak to peak is very small here. Peak to peak is very small, so the frequency of this one is very high. So meaning that, so for example, let's say I hit like this one time, and I just stand here, and I hit another time, and then I hit another time. So I'm doing hitting very slowly, right? One time I hit in once, maybe slowly, but this is less frequency. So if I hit like this, so this is more frequency. So how many peaks are there? So kind of you are hitting it. So this kind of one peak. So if you are doing this so many times, right? So this is a high frequency. So if you hit like this, less frequency. But if you hit like this, more frequency. So you are repeating the same thing many times in the short amount of time. Make sense? So like that. So frequency. So so this has a very small wavelength. So you have very small wavelength here. So large, you are repeating this many times. This peak many times within certain time. But you have very large, long wavelength. In this case, you are doing one time low frequency, another time like this. Yeah. So if you do something very fast, if you are drawing very fast, your frequency of moving your feet is higher. If you are walking slowly like that, your frequency of moving your leg is less. Yeah. So everything is a wave. Everything is a wavelength and frequency. So we'll talk about those later. Now, so this is the frequency. This is high frequency. This is low frequency. This is low wavelength. This is high wavelength. Now I have one quality, that is the velocity. That is velocity or speed. So velocity is given by c. So velocity is equals to frequency multiplied by the wavelength. So velocity c is equals to frequency, this number, and then multiply by the wavelength. So like this. Make sense? So these three things. So actually, wave has two characteristics. Only two characteristics. One is a wavelength, one is a frequency. How fast this peak are appearing is a frequency, and how long is the peak to peak distance is the wavelength. So that's only two characteristics wave have, and with these two characteristics we can define everything related to energy. Make sense? So only two characteristics. How many characteristics I need to identify me? Maybe one characteristic. So if I go to the police station, I give the thumbprint, right? And then they identify me as a thumbprint, right? So for the wave, we have two things: wavelength and the frequency. And from the wavelength and the frequency, we can identify everything. Now, like that one. So you can read yourself the first and the second slide. In the second slide, I have one more thing here. Let's draw a line somewhere in middle of this wave. Maybe the middle of this wave is somewhere here, right? So somewhere here. So I just draw the line at the middle of the this wave. So this distance from this mid position to this height. So this height. So mid position to this height. So mid position to this height. These heights. These heights are called the amplitude. Amplitude. Yeah. So if you see a very bright light, this is very big. The amplitude is very big. If that light is not like the dim light, the amplitude is low. Next. So go to the room and you have a very bright room, meaning that you have a lot of this number is the amplitude is very high. And go to the room, the light are very dim, is not lighting, there is no a lot of light, but still you can see something, right? So that has something like this. So let's say I make the same light. So this is maybe red light. This is also red light. But the wavelength between this peak and this peak is same. The wavelength between this peak and this peak and this peak and this peak is same. So this is also red. This is also red light, right? But what is the difference? If I go to the room, which is a very brightly red light, so like this. But if you go to the room, which is dimly red light, so it's a small. Make sense? So that's how they characterize all these things. Yeah. Good. So that's amplitude. Now we have. I'm in the slide number 3. So let's talk about the slide number 3. Now this one I have here. So white light is made up of 7 colors. So if you remember your high school chemistry book or physics book, like this is a prism. You have a prism there, and if you send this white light from this prism like this, send the light like this, and it goes here, and it is broken into 7, like 1, 2, 3, 4, 5, 6, 7, like this, 7 colors. So here is a violet light, and here is a red light. So violet, this is indigo, this is blue, this is green, this is orange, 1, 2, 3, 4, 5, 6, 7. This is yellow, this is orange, this is red. So one white light. So what is we seeing here in the room is a white light. Or if you go outside and look the light of the sun, that's a white light. So send the white light from the prism, then that breaks into 7 colors like this: violet, indigo, blue, green, yellow, orange, and red. Yeah. So all light start the same time from the sun, and they come same time on the earth. Yeah. So their speed is same. So the speed of this one, what is the speed? So the speed of violet, the speed of indigo, speed of blue, speed of this, all these kind of the light, all electromagnetic radiation have the same speed. Yeah. So they travel with this 3 multiplied by 10 to the power 8 meters in 1 second. 1 second. 1 second. So you have a stopwatch. So count the 1 second. So how much light or any electromagnetic radiation travel? 3 multiplied by 10 to the power 8 meter in 1 second. Make sense? So all electromagnetic radiation has the same speed, that is 3 multiplied by 10 to the power 8 meter per second. How is it possible? Let's look here. So there is a figure here I put from the website. So if you look this one, the red looks like this. So the red look like this. Like this. The red look like this. So it has large wavelength. So actually the distance between 2 peaks is always same. So like this. So distance between this peak and distance between this peak and distance between this peak and another peak is always same. Yeah, the wavelength. So what is the wavelength of the red light? So that is 665 nanometers. So if you measure from here to here, it is 665 nanometer. That means that, yeah. Or if you measure from here to here, that's also 665 nanometer. Now, let's go all the way to the blue. So blue looks like this. Like this. Blue looks like this. Yeah? Make sense? So what is the distance between peak to peak here? So the blue light would be 470. So from here to here, 470 nanometer. From here to here, 470. From here to here, 470, 470, 470. So the distance between the nearest two peak is the 470 nanometer. Make sense? So that's the wavelength. So red looks like this. So imagine like some father. So this guy is a father. So this is a this is a father. So this is a father, and he has long leg, yeah, like a long leg. Make sense? And then here is a daughter, like the blue. So this is a daughter. This is a daughter, and she has. This is a daughter here, and she has short leg here, right? Now they're starting to. This is long leg. So this is one leg, another. So it's kind of one leg. So you can move from here to here. What is the wavelength of the ray? The wavelength of the ray is 665 nanometer. 665 from here to here. 665 nanometer. So if you put a scale here and here, this measures 665 nanometer. Yeah, and so this blue looks like the daughter with a short leg, and this red looks like the father with a very long leg, right? Now they start to run. They start to walk like this. They are here and they want to move from this place to this place. So father move like maybe one pace, two pace, three pace from here to here, right? But the daughter should move how many paces? Many paces, right? So the daughter's frequency is very high. So she is moving her leg very fast, right? She is repeating her feet movement many times per second. So she has a high frequency. Make sense? So she has a very high frequency. This guy has a low frequency. But when they are moving together, they will reach this place at the same time. So they both have same speed. So father and daughter have same speed. Why same speed? Because father has a long wavelength. So father has a long wavelength. So his frequency is low. So he moves his foot slowly like this, right? Slowly like that. And then to follow her father, so the daughter whose legs are short, so she was just moving very fast like this, yeah. And then where they start at the same time at the beginning, and they reach to the another point at the same time. Make sense? So their velocity is, or the speed is same. Make sense? The speed is same. So this guy has large wavelength, large wavelength, and then less frequency, meaning that he didn't move his feet that fast. He moved slowly, right? But this lady, the girl has a small wavelength, meaning that she has a short leg, so she needs to move her foot many times to catch her father, right? So she is a small wavelength, but a high frequency. She move her feet many times per second. So how many times you move your feet per second, that is called the frequency. Yeah? Make sense? So what is the frequency? So the speed is same. Why the speed is same? All the electromagnetic radiation have same speed, although they have different wavelength and different frequency. Yeah? So how much time I have here? 44. So father was just moving like this. So he would do like this one time, and he wait for a while, and do like that, right? Father would do something like that when they are moving. But if you put something that gives a sound when while walking, the father would sound like that, right? Father one pace, and father would just do like that, right? So, but the daughter, she's just walking fast, just like that. Make sense? So this kind of instrument you can buy all in the internet, and then so if you put the red light, it clicks tick 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 for the red light. But if you put the violet or the blue light, sorry, the ultraviolet or the blue light, it ticks like tick 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 tick. It is very fast. Yeah. So they count the photon like that. Make sense? Good. So if ticks like put the light, it ticks very fast, that has a very high frequency. If ticks very slowly, that has a less frequency. Yeah? Good. Now, so let's look at, there is a YouTube video I posted in the link there. When you go home, you can just watch that video, that gives some idea. Yeah? So what I told you, just they are doing that one. So how to measure the frequency? So wavelength and frequency. So here is an instrument. So this is a, let's say this board is the screen of the instrument, right? Now you sit there and mark a point here. Mark a point here, like the line, and start to look. So now sit there and count. So I'm just looking here. So one peak passed through this one, right? And then I'm just here. Another peak passed through this point. Now see, I'm sitting and looking here, another peak passed through that point. And I was looking, let's say 1 second, within 1 second, 10 peaks passed through this point. So what is the frequency of that one? That's a 10 is the frequency. Make sense? How many times the peak passed through a certain point you are looking, that is the frequency of that light. Make sense? If it passed 10 times in 1 second, the frequency is 10 peaks per second. Make sense? If the 60 peaks pass through this point in 1 second, that's a 60 is the frequency per second. Make sense? So how many peaks pass through a certain point you are looking? So this is a big screen. I'm just looking here and I'm just counting how many peaks pass through this point. 1, 2, 3 in 1 second. Make sense? Good. So just like you go to the lake and make a point there, there's a stone there, and start to look that stone. One time wave comes and pass through the stone, the peak, right? And then again another wave comes and pass through that peak. Another wave comes and pass through that peak. So how many times the peak of the water pass through that stone in 1 second? That is called the frequency. Make sense? So it's a peak per second basically. They call cycle per second, or a complete wave passing through a point in 1 second, but it's basically the how many peaks pass through the 1 second is the frequency. Make sense? Good. So good. Now, alright. So I think we learned a lot. So we stop today here, and we do next class. So we have plenty of time. So we just finished 5 chapters. I have 4 more chapters, so they are not that long. Yeah. Good. Alright, everyone. Thank you very much. Here.